Alright everybody, welcome to section 14.7. We're going to be talking about maximum and minimum values for these multivariable functions. Alright, now I'm going to recall your attention back to Calc 1. Back in Calc 1, we were trying to identify some of these maximum and minimum values for these different functions. Alright. Now, just as a quick, let's say, example, I'll give you one on screen here. Let me now rotate this. As you can see, I'm getting kind of slightly better. Still not quite, but it's a work in progress. We're getting there. Alright, there we go. That looks about good. Now, back from Calc 1, we were focused more on, let's say, finding these maximum and minimum values that were associated to the graph. Now, if the graph was given a specific interval, then we could say this here was an absolute minimum for f of x. Here we would say we have a local max, and again it's a local max specifically because as we're looking at this function goes further higher on the y values, and this here was known as your local min. Right, now the different ways to get this, or the different ways to see this, was to take derivatives. We typically took one derivative, or the first derivative, so that we can find these intervals of increasing or decreasing, and the second derivative then told us about concavity. When were we concave up, when were we concave down? Now, unfortunately for multivariable, it doesn't exactly work the same way, but we can get the same interpretation using different methods. Those different methods are going to seem very familiar because they still involve us working with taking a first and second derivative for this function that we're working with. So before I go further, let me go ahead and let me actually define what it is to be a local max, local min, and then we'll take it from there. Alright, so here we go. Alright, so here's the definition that we're going to be working with. This definition says that a function of two variables has a local maximum at the point AB, and again this is going to be a point in the domain of the function if, when we evaluate that point of the function, it is the highest point around that region. And that's what this definition says here, or this symbol says here. Alright, so the number f of AB, in other words, the z value, or the output of the function when evaluated at the given point in its domain, that's called the local maximum value. Now, I want you to take some time and digest these definitions. Alright, we're going to be working with them. And I want to give you a quick visual of what it means to be a maximum or minimum when we're looking at these multivariable functions. So here we are, looking at my old friend GeoGebra here. Alright, so I took the liberty of graphing this surface, and you'll see the equation of the surface on the left-hand side over here of the screen. So using that equation, I also plotted 2 points on here. Look at point B. Point B kind of looks like this maximum, but point B is not the absolute max because there's other values, other z values that are larger than it. However, on a small area, on a small region, that point for B is actually the largest possible, which then makes it a local max for this function. Now, looking at the next point A. Point A is slightly different because if you notice, if I reorient my axis, let's say this way, then to the left of the point A, it's increasing. To the right, it's increasing. But what happens if I orient it this way and I look at it this way? What happens to the left of point A? Well, to the left of point A, we now decrease, and to the right of point A, we now decrease. Which means point A is neither a maximum nor a minimum. Point A is what we call a saddle. So we have to make sure that when we're looking at these, let's say, critical points or these critical values that we get, we must be able to interpret them in some way to determine whether they will produce a maximum, a minimum, or what we call a saddle. Alright, so let's go back to the notes. Alright, so very similar to Calc 1, what we're going to need to do to find these maximums or these minimums, or in our case, these saddle points, we must first develop a method to locate them. And the way we want to do that is we want to do that by using derivatives. We want to identify these by using the first derivative. Alright, so I'm going to write down a definition that we have, and that definition is going to get us what this critical point is going to look like. So here's the definition that we're working with. It says that an interior point of the domain of a function, f of x, y, where both partial derivatives, f partial of x and f partial of y, are 0, or where both of the partial derivatives do not exist, is going to be known as a critical point. Alright, so what we want to do is we want to establish, or we want to work with this, that way we can find these critical points that were given. Alright, so let's do a quick example then. Let's see if we can find the critical points. So here's the example. It says find the critical point for this function. It's x squared plus y squared minus 4y plus 9. So since we want to find the critical point, what we're going to have to do is we're going to have to use the definition to say that we need these partial derivatives. So I'm going to take my partial derivative with respect to x first. So taking that partial derivative with respect to x first is going to give me 2x. Then taking my partial derivative with respect to y, that should get me 2y minus 4. There we are. Now, according to this definition here, now these will not be undefined because we're dealing with a polynomial function. Therefore, it must be wherever they are 0. Which means the first pair here that we get is x is equal to 0. And then the second pair that we get over here, or the second value that we get, is that y is equal to 2. Therefore, using this, we get that the critical point is the ordered pair 0, 2. And that's it. That is all that we need. The x value was from here. The y value was from there that we found. And that's all that we really need for these for this derivative test, is that for this derivative test that we're going to be making. So all we need to know is how to find those critical points at this point in time. Alright, now let's see if we can elaborate just a little bit more as to how we're then going to start classifying these particular points. So what I'm going to go into next is what is known as your second derivatives test. Alright, so I'm going to take some time, I'm going to write it down, that way we can then just go through and talk about it. Alright, so here's the definition that we're using for the second derivatives test. Now, please be very careful with the pronunciation for this because we're looking at the second derivatives test, not to be confused with the second derivative test. This is plural, derivatives. And the reason it's plural is because we're using all of the different combinations that we have for the second order partial derivatives for this multivariable function. So the thing that we have here says that suppose the second partial derivatives of a function are continuous on a disk that we center around the point AB. And suppose that the partial derivative of the function with respect to x is equal to 0, and the partial derivative of the function f with respect to y is also equal to 0. Then we want to identify the determinant here. This determinant, and I'm going to write this is a determinant, is this part that follows this formula here. So we need to find the second order partial derivatives for the function, both with respect to x and with respect to y, and then we also need to find the mixed second order partial derivative. As soon as we do that, we use this equation to give us the determinants that we need. Now, part A. Part A is going to tell us if that determinant is greater than 0 and if the second order partial derivative both with respect to x is greater than 0, then the function is going to have a local minimum. Similarly, determinant greater than 0, except this time second order partial derivative for x is less than 0, then we're going to have a local maximum. Now, this should kind of stand to reason that this part here should remind you of the second derivative test from Calc 1, letting us know about concavity. If we have a function that is concave up, then we have a local min. If we have a function that's concave down, then we have a local max. So again, this still falls under the whole category of this looks very, very similar, and again, it should have that similar feel because we're still looking at derivatives. If the main determinant is less than 0, then our function has a saddle point. So that's going to be very nice for us that any time that our determinant comes out to be 0, hey, we have a saddle point. Anytime that the determinant comes out to be exactly 0, then the test is going to be inconclusive, and we're going to have to use other methods to make sure that we can find those maximums, minimums, or saddle points. All right, so part D we kind of never want to get, but if we do, then we'll take some methods of approach there. All right, now I keep calling this piece up here the determinant. Why is it known as the determinant? Well, it's known as a determinant specifically because it has this determinant feel, or we can set this up in the form of a determinant if we look at the partial derivatives for this function, and if we put these partial derivatives in matrix form, we can use their derivatives. We can use the determinant of these derivatives to make sure that we get our specific determinant here, or formula. To find this determinant, we multiply this derivative times this one, so that's f double prime with x, f double prime with y, multiply these two, that was this first piece here, minus these two pieces multiplied together. But remember, by Clay-Ruth's theorem, Clay-Ruth's theorem says that if these two are continuous partial derivatives, then what we're going to have is that these two must be equal to one another. So naturally, we're going to have those two portions here. Now, since we're requiring that the second order partial derivatives must be continuous, then Clay-Ruth's theorem is active here, and they will both be equal to one another. All right, so there we are. So now what we want to do is we want to use this specific example, we want to use this specific theorem to make sure that we can generate these examples, and we can start classifying these examples to see what we get. All right, so here goes your first example. Oops, there we are, example. All right, so we want to find the, I'm going to say extreme values of this function f of xy, which is 3y squared minus 2y cubed minus 3x squared plus 6xy. So let's find all these extreme values. Now, really quickly before I start, I want to say that anytime that they're asking you to find extreme values or extremums or anything like that, what they're really asking you to do is find all maximums or minimums, whether they be local or absolute. So it's kind of like again, one of those loaded questions that says, hey, we have a lot of stuff embedded in here and we need to extract everything. So if on my exam you see that I need you to find these extreme values, it means, hey, you need to find maximums, you need to find minimums, and are they local and are they absolute? All right, so to start off here, we're going to go through and we're going to find partial derivatives. So let's find the first partial derivative here. I'm going to say the partial derivative with respect to x, that's going to be right here, that's going to be negative 6x plus 6y. Awesome. I need to find the partial derivative for my function with respect to y. So I'm going to do that here, partial derivative. There we go. So that's going to be 6y minus 6y squared plus 6x. There we go. Now all we have to do is set these equal to 0. All right, so let's set them equal to 0 and see what we get. This is negative 6x plus 6y. This is 0 is equal to 6y minus 6y squared plus 6x. There we go. We got to try to solve for x and y. See if we can get that to happen here. All right. Let's see what we're going to do. I see a 6x over here, so I want to get that 6x by itself right here. So I'm going to use 6x here is equal to 6y. There we are. And what I'm going to use now is I'm going to use substitution. All right. I'm going to say substitution. And when I use substitution here, I know that I have this 6x. This 6x is now going to be interpreted as this 6y, all right, by what we have over here, which then means that we have 12y minus 6y squared is equal to 0, which then gives us, let me see, I can factor out a 2y from there, and that will be leaving us with 6 minus call that, what was that, 3y? Let's see, oh, nope, sorry, my apologies. I'm having a brain fart moment. I can factor out a 6y, there we are. And that works out way better. This will leave me with 2, and then this will leave me with minus y. Perfect. There we are. All right, good so far? Awesome. So what we get here is we get two different values for y. So we get that 6y is equal to 0 or 2 minus y is equal to 0, which means y is equal to 2 or y is equal to 0. Now, using these two values, what I want to do then is I want to figure out what are the x values. So I'm going to go through and I'm going to find out what those x values need to be in order for this to be satisfied. All right, so I'm going to use y is equal to 0. So if I use y is equal to 0 on this substitution here, where we had 6x is equal to 6 times 0, then we're naturally going to get that x is equal to 0. And then if we use y is equal to 2, then using y is equal to 2, we get 6x is equal to 6 times 2, which means this is going to be 12 divided by 6. We get that x is 2. Nice. So the first values over here that we get was that x is equal to 0 and y was equal to 0. The second ones that we get were x is equal to 2 and y is equal to 2. Nice. These are the critical points that we need. All right, so we found critical points. Yay. That's what we need. Now that we've found those critical points, we can go through the whole classification aspect of this. So to go through the whole classification aspect, we're going to need to know a few things. All right. So I'm going to make a quick chart or a quick table in order for me to organize my information here. I would highly encourage you all to do the same. That way we can keep this information compact and, again, organized. So I'm going to have my ordered pair. So I'm going to have my x's and y's. I'm also going to want my second order partial derivative here. My second order partial derivative for y. Oops. I'm also going to want my mixed partial derivative. Excuse me, I keep putting AB. Now technically it wouldn't be wrong with AB, but geez, I want continuity here. I want to stay exactly the same. See, there we go. Wow, that's a third mistake right there. There we go, XY. And now we want the actual determinant. So we want the actual determinant, and we'll figure out what that determinant is in just a bit. All right, here we go. So my first ordered pair was 0, 0. Second ordered pair was 2, 2. Now we need the second order partial derivatives. I don't think we've calculated that yet. So I'm going to go through and I'm going to make some of these calculations here. So f double prime of x. F double prime, if we look at f double prime, that's going to be what, -6? Nice. F double prime at y. F double prime with respect to y, we should be able to get, let me find it here, so that's going to be 6 minus 12y. So the double prime, that was the 6 minus 12y. And the mixed derivative, that should just be 6 by itself. There we are. All right, perfect. So let's go through our substitutions. Since the double prime derivative for x is always going to be a constant, it's always going to be -6. So I'm going to fill that in there. The other constant that's going to be here is these 6's. Great. And the final derivative is this one right in the middle. I need to go ahead and evaluate. So what I'm going to do is I'm going to substitute the x and y values for the ordered pairs into the actual derivative here. So if y was 0, that's y is 0 here, which means we get a derivative of 6. And if y is 2, then y is 2 here, so that's going to be -2 times 12. That's going to be -24. So then that's going to be 6 minus 24. All right. So 6 minus 24. So we should get 18 there. Nice. Now to find this determinant, all I want to do is start getting all these numbers together. So it's going to be -6 times 6 minus 6 squared. And this is my main determinant. So this is going to be -36 minus 36, which should get us -72. Nice. And then the other one should get us -6 times 18 minus 6 squared. All right, so again, we can go through on the calculator here. So it's going to be -6 times 18 minus that 36. It should get us -144. There we are. And my apologies, I just realized I did something wrong. Really excuse me here. This is supposed to be a negative. That means this is a negative. Negative times a negative is going to get me that positive. And when we multiply this, we should get positive 72 for this one here. My apologies. Very big apologies for me there. So 72, there we are. Awesome. So we can then see, using this determinant process, this determinant here is less than 0, this determinant is greater than 0. Now, if you remember back by the definition, we can then go through. If the derivative is less than 0, if the determinant is less than 0 at any point in time, then we have a saddle. So, where do we have a saddle? We have a saddle at 0, 0. What does this then tell us? Well, since the main determinant is greater than 0, that means we do have some type of local max or local min. Then we look at the second derivative with respect to x, and we see that that one is negative. Since it's negative, it kind of tells me it's concave down, which means we're going to have some sort of maximum value. So here we do see a maximum value, and it's going to happen at this ordered pair 2, 2. So really quickly, I'm going to summarize here. I'm going to say saddle and local max. So my summary, and this is what I want to see. I'm going to be looking for the summary on every single question that I ask you for the exam. All right, so here goes my summary. F of x has a saddle point at 0, 0 and a local max of, and I need to write down what is that number that produces that local maximum. In order to find out what number is that local maximum, we need the actual function. We need to evaluate the actual function at the given point. So in order for me to finish summarizing this, I need to then figure out what is that value. So I'm going to go to my function and I'm going to substitute in f of 2, 2. So substituting this in, we'll get 3 times 2 squared minus 2 times 2 cubed minus 2 times 2 squared plus 6 times 2 times 2. Now, going through this, let's see, 2 squared, that's going to be 4, so it's going to be 4 times 3, that's 12. The next one's going to be 2 cubed, that's 8. 8 times 2, that's going to be 16. The next one's going to be 4. 4 times 2, that's 8. The next one's going to be 6 times 2, that's 12. Times another 2, that's going to be 24. So here we have 12 minus 16 minus 8 plus 24, and we get 12. There we are. All right. Now, let me just double check my work. 12 minus 16. Let's see. Did I miss something here? Ooh, yes. My apologies. 3x squared. Oh my goodness. I am just riddled with a lot of inconsistencies today. I don't know why. There was a mistake here. Now, luckily, I'm following some of my notes. That way I can go through this and find some of my issues here. But here, yes, there we go. So it's negative 16 plus 24, and that should be 8. There we are. So here, we, again, then just going back to the summary, we're going to say, and it has a local maximum of 8. So that's a local maximum. And now I have to state where that local maximum occurs. So it has maximum of 8 at the point 2, 2. There we are. So this is what I want to see when I'm grading. I want to see this specific verbiage saying, hey, I went through the process, I went through the whole work, I showed my work, and then I summarized it to give you my local maximum and the saddle point. All right? Awesome. So typically I would ask in class, are there any questions? And probably after all those mistakes, I would say, hey, let's go on break really quick. But since we're all, in our own places, we're not going to take a break and we're going to continue going. Again, needless to say, if you need to take a break, please go ahead and take a break. All right. So let's see if we can try a different type of question that's going to be slightly, just again, slightly different. All right, so here we go. Here's your example. We want to find the critical points of the function f of xy, which is equal to x squared plus y squared times e to the negative power of x, and analyze them using the second derivatives test. All right, so here we are. Now, in order to be able to do this, again, we need to go through and we need to find these partial derivatives. So let's go through and let's find these partial derivatives. So f prime with respect to x. F prime with respect to x. Notice here we're going to need our product rule to be able to take these derivatives. I still don't like that too. There we go. All right, so derivative of the first function, that's this one with respect to x. So that's going to be 2x, taking that derivative, there we go, multiplied by e to the power of negative x. Nice. Plus the first function, which is x squared plus y squared, multiplied by the derivative of e to the negative x, and that's just going to be negative e to the negative x. There we are. I need to find a first derivative with respect to y. This one's kind of nice. All right, so let's go ahead and let's take the derivative here. All right, and then here we should have 2y e to the negative x. And I do believe, let me just double check, if we distribute this in, then the x's are just constants, and this is the only derivative. Perfect. All right. So what we need to do then is we need to use the critical points. So let's go ahead and let's find when these are equal to 0. So I see these both have e to the x, and I'll come back to that. So that's going to be 2x e to the negative x. Minus e to the negative x times x squared plus y squared. And then this one's also going to be 0 is equal to 2y e to the negative x. There we are. And instead of working with the left side, I think I want to work with the right side. It gives me a little bit, with the rightmost equation, it gives me a little bit more details, more insight as to what I need. Because this here is then going to tell me that 0 is equal to 2y, or it tells me that 0 is equal to e to the power of negative x. And if you notice anything about this, e to the power of negative x, I don't think this ever gives me 0, right? You could look at this when you're graphing, when we're looking at a graph of e to the x. When we're looking at a graph of e to the x, it never crosses the x-axis, and because it never crosses the x-axis, we could then say that the value never takes on y is equal to 0, and since it never takes on y is equal to 0, or in this case where x is equal to 0, then we don't need to worry about it. All right, and again, I'm just giving you a really quick sketch. All right, negative just means that we're going to reflect all of those values, which means it looks like something like this. This is a graph of e to the negative x. And you'll see here that the graph of e to negative x never crosses this axis, which means y is never equal to 0 when we're looking at this function, which means this does not occur. Which means the only possibility must be that y is equal to 0. So if y is equal to 0, then we're going to use substitution to see if we can find those values here. So I'm going to use substitution. So let's go with that substitution. So this is 0 is equal to 2x e to the negative x minus e to the negative x. And we have x squared plus, we're going to insert what we know about that. That's going to be 0. And all we have to do here is solve, which is kind of nice because, again, we wind up with the same process. I'm going to factor out e to the negative x, and we have 2x minus x squared. There we are. And then once again, we go through the process of saying e to the negative x must be equal to 0, or 0 must be equal to 2x minus x squared. Now we know from our previous work does not occur, so that kind of goes away, which means here we're going to be looking at 2 minus x, which means x is equal to 0 or x is equal to 2. Nice. Wow, that was a lot of work. That was a lot of work. So notice what was happening here. What we did here is that we used y was equal to 0 here. And when y is equal to 0, we followed this whole path, which gave us two different solutions or two different ordered values for when we use y is equal to 0. So the critical points. The critical points here, we get x is equal to 0, but under the assumption that y was equal to 0. We also get that x is equal to 2, but under the assumption that y was 0. So these are the two values that we need for this problem. X is equal to 0, y is equal to 0, x is equal to 2, y is equal to 0. So let's go ahead now and let's organize our information, find those second derivatives, and work with that process. All right, so on this side of, I was going to say on this side of the board, technically it's correct, but you know what, we'll leave it as is. So I want to find the second derivatives. So I'm going to finish finding those second derivatives. All right, I'm going to find f double prime with x for xy. All right, so looking at the first term here, using the first term, I need to go ahead and I need to use the product rule. So derivative of the first function, which is going to be just that 2x. So derivative is just 2 multiplied by e to the negative x, plus the first function, which was 2x, multiplied by the derivative of the second function, which is negative e to the power of negative x. There we are, that was the second derivative there. All right, so plus. Now this derivative with respect to x, we're going to have to use a product rule there again. So let's go ahead and let's use that product rule. So derivative of the first function, all right, so let's do the derivative of this with respect to x. That's just 2x multiplied by the second function, which was negative e to the negative x, according to this. Now, first function, so plus x squared plus y squared, multiplied by the derivative of the second function, and that's just going to be e to the negative x. Wow, that's a really long derivative. But let's go ahead and let's clean that up. All right, so again, got to clean this up. So let's see, I believe we have some like terms here. So that should be 2e to the negative x minus, that's going to be 4x e to the negative x plus x squared plus y squared times e to the negative x. There we are. All right, not too bad. All right, let's work on the next partial derivative. So the next second order partial derivative, I'm going to want with respect to y both times. All right, so with respect to y both times in this particular case, That's just going to be 2e to the negative x. Great. And then I also want my mixed derivative. And again, Clairaut's theorem is just going to justify that we get the same derivative regardless. So looking here, we want this derivative with respect to x. So this derivative with respect to x will now be negative 2ye to the negative x. There we are. So let's start making our table to make sure that this is all ordered nicely. All right. So I'm going to make myself a nice little table here, and let's see if we can work through it. Yeah, just bear with me. Moving this ruler around. There we are. Come on. There we go. All right, perfect. And then let's turn it around. There we are. And I want some values in here. Well, let's actually go a little bit higher. There. Perfect. And that way I can start inserting my values here. Nice. All right, up here I want, oops. Up here, I'm going to have my ordered pairs. So my ordered pairs, let's erase that, my apologies. So my ordered pairs are going to be, there we go, wow. All the xy's, this is going to be the second order partial derivative. This is going to be the second order partial derivative for y. This is going to be my mixed derivative, and then this is going to be my determinant for x's and y's. All right, so let's go through this process. The first ordered pair that we're going to be looking at is going to be 0, 0. So I'm going to have 0, 0. And the next one after that is going to be 2, 0. My apologies. I was making this table for too long, trying to justify this. I, for some reason, had imagined 3 points in my head, but apparently it's 2 points. So, yay. All right, here we go. Wow, I know, Mr. Castro is way off today, but it's okay. And I really hate referring to myself in a third person, but sometimes when things aren't going my way, it's okay. All right, here we go. So, second derivative with respect to x evaluated using 0, 0. So I'm going to insert x is 0, x is 0, x is 0, and y is 0. So 0 times 0, 0 plus 0, that's 0. So this is going to get me 0, that's 0. And this here is just going to get me 2 times 1. So this is going to get me just 2. All right, now f double prime with respect to x, again, inserting a 0 there, it gets me a 2. Nice. Mixed derivative now gets me 0. All right, so to find this determinant, all I have to do is multiply, and then subtract out the square. So when I do this, this is going to get me 2 times 2 minus 0 squared. Then that's just going to get me 4, and that's greater than 0, which is good. Nice. So next one, f double prime of x is 2, y is 0. So x is 2, so that's going to get me something weird. X is 2, again something weird. X is 2. All right, so let's go through and let's actually formalize this just a little bit more instead of saying that it's going to get me weird or anything like that. So here we go. So f double prime at x using 2, 0. This is going to get me 2 e to the power of negative 2 minus 8 e to the power of negative 2 plus 4 times e to the power of negative 2. All right. Doesn't look too bad here. So it's at 4, that's 6, negative, so it's going to be negative 2 e to the power of negative 2. In other words, we're looking at negative 2 e squared. So negative 2e squared, or negative 2 to the power of negative 2. So that goes in here, like such. F double prime at y, so f double prime at y, so that's going to be 2 times e to the power of negative 2, so that's just going to be, or sorry, e to the power of cheese and crackers. Here we go. So this one here is going to just be 2e to the power of negative 2. Working with the last one, y is 0, which means that's going to be 0. So now we multiply negative 2e to the negative 2, and then 2e to the negative 2 minus 0 squared. This is now going to get me negative 4e to the negative 4. E to the negative 4, again, that's value is always going to be constant, and that's, positive, which means negative 4 is the one that makes us less than 0. Which means by our determinants, what we have here is we have a saddle. This determinant was greater than 0, which is good, so this is going to produce either a local max or local min. Then we go to f double prime at x and look at this. Since it's positive, that means it's going to be concave up, but since it's concave up, that means we're going to have a local minimum. So this in here is going to produce a local min. All right, so let's go ahead and let's summarize. F of xy has a saddle point at 2, 0 and a local minimum of, and again, I want to figure out what is that local minimum. So in order to figure out what is that local minimum, we need to go through and we need to actually figure out what is that value. So again, just doing some work on my actual function, I'm going to insert the actual ordered pair into the function. So the function that was 2 squared plus 0 squared times e to the negative 2. All right, and this just gets us 4e to the negative 2. And that right there is this local minimum, which is 4e to the negative 2. So local minimum of 4e to the negative 2, and that happens at the ordered pair 0, 0. And there we have it. All right. So as we go through this, again, we have to rely on our process to be able to find these derivatives and interpret what we're observing. So the very last item that we want to touch on here is going to be the item when we look at what is known as our extreme value theorem. Now, for that, what I would want to do is I would want to once again call on Calc 1. Because again, almost everything that we're doing in here is based off of Calc 1. So if we know how to work with the process that we learned back in Calc 1, then these processes shouldn't be too far of a stretch. All right, so here's my y values and here's my x values. And for some reason my stylus doesn't want to work, it's okay. So say if we had some function f of x back in Calc 1. All right, so if we had some function f of x, we could put an interval around this function, call it from a to b. And just looking at this interval, we could then start interpreting what is the local maximum, what is the local minimum, but we can do more than that. We can actually find what is the maximum value and what is the minimum value given that interval for that function. Which means we need to go through and we need to use a derivative in order to be able to find that absolute minimum. And then we also need to use, if the derivative gets us that derivative or that value to be the maximum, then great. If not, then we might need to use the endpoints. So when we look at this, and I'm going to say that this is your absolute max, all right? So when we start looking at this, we always have to be aware that given an interval on a function, we can and we will have these absolute maximums and minimums, and we have to find them. What does that mean for us, though? Well, we're going to have what is known as the extreme value theorem for a function of two variables. And that's the item that we're working on in this section. That's actually going to be the last item or the last topic that we focus on in this section. So this is known as your extreme value theorem for functions of two variables. Whoops. There we go. All right, perfect. For some reason, you can never line it up again. It's okay. So here we go. So the extreme value theorem for the functions of two variables. So I'm going to put a pause on this video. I'm going to fill it in, and then we'll come back and we'll talk about it. All right, here we go. So here's your extreme value theorem for functions of two variables. So these extreme value theorems, this extreme value theorem again says that if we have a continuous function that is closed and bounded on some set D, and that set D is some region in R space 2, then the function attains an absolute maximum or an absolute value, or an absolute minimum value at some points that exist within that domain or within that region. So that just means for us that we then have to investigate what are those extreme values. Does it have absolute maximums or minimums? And if it does, then we have to find them. So here's the question. We want to find the absolute maximum and minimum values of this function f of xy, which is given by 3xy minus 6x plus 3y plus 7. On the closed triangular region R with vertices 0, 0, 0, 5, and 3, 0. So again, we're trying to find the absolute maximum, minimum values for that function, and we're given that the region that we are being bounded by is this triangle with these given vertices. All right. So, that's a lot of work. That's okay. Let's go through and let's draw the region first. All right. So that's the first thing I want to do is I want to sketch the region. So sketch the region. All right. Let's go ahead and let's sketch that region. All right, here we go. I'm going to have my ruler once again. All right, let's see. That's 0, 0. Then it's going to be 0, 5. Then it's going to be 3, 0. So that's going to be in the first quadrant. All right, let's actually go down a little bit more. There we are. So it's going to be in the first quadrant. Nice. Let me see. Go 90 degrees. And let's go a little bit back. Here we are. All right, that seems about good. So that's 1, 2, 3, 4, and 5. There we go. And then we're going to have our x values here, and that's going to be again 1, 2, and 3. Perfect. All right, so the vertices goes from 0, 5 all the way to 3, 0. So that's going to go from there all the way to down there. So we're just going to go ahead and we're going to construct that line to show that region. All right, there we go. And it went from here to here. So this is the region that we are focusing on. There we are. So now that we have the region, let's go ahead and let's find these derivatives. So let's go through and let's find these derivatives. I'm actually going to shorten this up. I don't want it to take too much room. There we go. And I forgot to label that. That's why. Perfect. So let's find the derivative. Partial with respect to x. Partial with respect to x for this function, that's going to be 3y minus 6. Partial with respect to y, that's going to be 3x plus 3. Set both of these equal to 0. So it's going to be 0 is equal to 3y minus 6. 0 is equal to 3x plus 3. We get here that x is equal to negative 1. And we get here that y is equal to 2. Which means my critical point, I'm abbreviating critical point as a CP, and that's going to be my x value of negative 1, y value at 2. So let's find that critical point here, 1, 2. So that's going to be right in here. Now the big question is, does it fall within that area? And, oh, my apologies. Wow, see, I'm way off today. I really apologize for that. Now, the critical point is negative 1, 2. Negative 1 falls here, and then 2 falls here, which means, is this critical point within our region? The answer is no. Not in the given region. So because it's not in the given region, we don't have to use it. So when we're going through at the very end, analyzing all of our critical points or all of our points, this is one point that we do not use because, again, it is not within that region. Nice. So all that we get to do now is we have to go through and we have to then start analyzing all of the boundaries. So that's step number 2. We want to analyze the boundaries. So let's look at those boundaries. And I'm going to highlight the boundaries, or let's say I'm going to mark the boundaries with different colors. The first boundary for this region is right here. And that equation for that boundary, I'm going to call that, let's call that curve 1. Curve 1 has an equation of x is equal to 0, and this only works for the y values that are bounded between 0 and 5. Curve number 2. Let's analyze curve number 2. This is curve number 2 here that I'm highlighting. So that's curve 2. We need to find the equation for curve 2. Luckily, we kind of already have the equation given to us. We can use slope-intercept form. Slope-intercept form says I need to know what is the intercept, y-intercept, that's 5. So that's plus 5. And then the slope is the rise over the run. So that's 5 over 3. So that's 5 over 3x. There we go. And this only works for the x values that are bounded between 0 and 3. Next curve. The next curve that I have, let's see, what color do I want to use? I think I want to use, I don't want to use green. Let's use light blue. So this is the last curve that we want here. That's curve number 3. Curve number 3, the equation for that is y is equal to 0, but that only works for the x values that are bounded between 0 and 3. There we are. So this is all that we need. We need to test these boundaries. So, how do we go about testing these boundaries? Well, in order to analyze them and to test them, we have to substitute them. Substitute into the actual function f of xy. Now, what this is going to do, when we actually substitute them into the function, what it's doing is it's fixing that plane or that surface to cross this function, and in a sense, you're parametrizing that intersection. And when you parameterize that intersection, you're actually moving all of these two variables into one variable, which then makes it easy to analyze where's the maximum and where's the minimum. So let's work with that analyzation of the boundaries. So I'm going to work with the first one, which was my x is equal to 0. So curve number 1. Curve number 1, x is equal to 0, and that was for the y values being bounded. So here goes my function. I had my function f of xy, but again, I don't have f of xy anymore because I'm using x as 0. So this is going to be x at 0. Y stays exactly the same. All right, I'm not going to change any y's. They are going to change between 0 and 5, but we'll hold off on that. All right, so this means this is going to be 3 times 0 times y minus 6 times 0 minus 3y plus 7. All right, this actually cleans up real nice to just leave us with negative 3y plus 7, like such. Now, would you agree that this function here, that negative 3y plus 7, is just a one variable function? Sure is. That one variable function, it can only change from 0 to 5. So, using these restrictions from 0 to 5, what is the maximum and the minimum that this value, this negative 3y plus 7, can get? All right, so that's a question. Well, that question is actually nice. Because this is linear, it will either happen when y is 0, or it's going to happen when y is 5. Either way, we get some really nice answers here. Negative 3 times 5, that's going to be what, 15, and then plus 7, that should get us 8. So that's going to get us at negative 8. There we are. So as far as our boundaries go, the boundary for the first curve gets us these two values that we get to observe. And again, because this function moves linearly. Second function, C2. So curve number 2. Curve number 2, we're going to have y is equal to 5/3 x plus 5. And this is going to be for the x values that are bounded between 0 and 3. So let's go to the function. We're going to have this function f x. I'm not making any substitutions for x's right now, but my y values are changing into this function. So that means when I substitute it into my function, I get 3x times y, but my y value is now this linear function, minus 6 times x, minus 3 times y, there we are, plus 7. Right, there we are. So all we need to do now is just go ahead and condense everything. So let's see if we can condense everything here. So multiply by 3 in here, so that's going to be 5x squared plus 15x minus 6x. Multiply, that's going to be minus 5x minus 15 plus 7. All right. Looking good so far. That's 5x squared. I see a 15x, and I see a negative 6, and I also see a negative 5x. Alright, so making sure I make my subtractions there, so I should get 4. So it's just going to be plus 4x. There we are. And then I see a negative 15 and a 7, so I believe that should be negative 8. There we are. Perfect. So we have this function now. Now, would you agree that this function is just a parabola? All right, yeah, I would agree too. All right, so I'm going to actually put a comment on here. This is a parabola. Use derivative, use, I'm going to say calc 1 to find max or min. Okay, so what I'm going to do here is I'm going to label a new function. I'm going to call this new function, let's say g of x. Again, I'm just choosing a different label, pull that out of thin air with the same variable that I'm using, and I'm going to use calculus here to take a derivative to see what the maximization here will be. So it's going to be 10x plus 4. When I take that derivative, setting this equal to 0 will then get me 10x plus 4, which means that x is going to be negative 4 divided by 10. Negative 4 divided by 10 should be 2/5, so that's negative 2/5. All right. It's not looking too bad. All right, so once we get this x value, we're then going to be able to see that this x value not in the given region, because the given region is only defined for x values between 0 and 3. So for this to be maximized doesn't happen, or the vertex doesn't happen within the region. However, we still need to go through and we still need to test the boundaries for this particular function. So this function that we have here, we got by saying we're going to transcribe these x values, and these x values in our case are only going to be 0 and 3. So the x values are only 0 and 3. So what's going to happen if this y value has an x value of 0? Well, then we just get 5. What's going to happen here if the x value is 3? Well, if the x value is fixed at 3, this is just going to be 5 plus 5, which is going to be 10. All right. So looking at this function here then, looking at this function, I'm going to be able to then make my inputs, right? What is going to be x and what is going to be y when I'm looking at these inputs here. All right, so let's go through those calculations really quick to see what we get. Now, in the grand scheme of things, again, there's another typo here that I did not catch. Some of you all might have caught it. I did not until I was doing my calculations right now that I realized that this isn't coming out the way that I had initially crafted it to. And the reason being is because there is a mistake right in here. This is supposed to be a negative slope. If it's a negative slope, then this changes, oops, excuse me. Then this piece here changes to negative 5x squared. All right, I'm just going to make my changes here. Negative times a negative, that's going to be positive. So that's positive 5x. And that distributes, it's still going to be the same, so that's not too bad. So then this is a negative 5x squared. And then this in here is going to be 20 minus 6, so that's going to be 14. And I believe that's the last spot I should have a negative on. All right, so then that's going to be plus 14, which means that's now going to get me negative 10 plus 14. So then 10 divided by 14, that's going to get me 5/7. And that sounds a little bit more realistic. Now, I was wondering why I crafted this so that it wouldn't be in the domain, which was kind of weird. So that's, yeah, that's just positive. So that's positive 5/7. There we go. All right, so x is equal to 5/7. Now, again, back to the drawing board here because these are now incorrect here. There we go. So, what I'm going to be using here, there we are, the x value of 0 here and the x value of 3. Well, if x is 0, plugging it in here, we still get 5. Nice. All right, so that didn't change too much there. And if x is 3, then x being 3, that's going to be 3 times 5, or sorry, 3 times 1/3, so that's going to be negative 5 here. So negative 5 plus 5, that's just going to get me 0. Perfect. All right, so now substituting this into my function, my y values are zeros, and then my x value is a 3. So that's going to be negative 18. Negative 18 plus 7. Negative 18 plus 7 should get me that negative 11. 0 and 5. So x is 0. X is 0. 5. So that's going to be negative 8. All right, not too bad. There we are. Great. So that was curve number 2. And again, my apologies there. But now that we got it all sorted out, that's great. All right. And I had one more. That was 5/7. So if x is 5/7, I need to find out what y is. That way I can find out what output I have. So if x is 5/7, according to the work that I just did, and I'm going to, let's say, highlight this in green. There we are, 5/7. Let's figure out what y is. All right, so x is 5/7 here, so that's going to be 25, if I believe, 25. Whoops. Cheese and crackers. You know what? I think I'm done for the day. I've already made way too many mistakes. This is actually 14 divided by 10. 14 divided by 10 is 7/5. Come on, man. My apologies. I have no idea. It's just another Monday. Oh my goodness. So 7/5 multiplied by 5/3. 5 and 5 so will cancel. That's going to be leaving us with 7/3, which is negative. So negative 7/3. Negative 7/3 plus 5 gives us 8/3. There we go. So now we're going to make this substitution into our function. So substitute this into the function and see what we get. All right, let's see, this is going to be 3 times 7/5 times 8/3 minus 6 times x minus 3 times y plus 7. There we are. All right, so at the end I get something along the lines of 9/5. All right, nice. Now let's check out curve number 3. Oh my goodness. Okay, so here we go, curve number 3. So curve number 3 we're given as y is equal to 0, and this is going to be for the x values that are between 0 and 3. Now this one again is going to be slightly easier because when we do our substitution, the x values don't change, the y values just become 0, and within this process we're just left with negative 6x plus 7. And again, this is just a linear function, so because it's a linear function, it's going to attain the maximum and the minimum at its endpoints. So when x is 0 by the given here, and when x is 3 by the given here, the y values don't change. If the x value is 0, then we get 7. If the x value is 3, then we get negative 18. Negative 18 plus 7, that's going to be the negative 11 that we have. So let's start ordering all of this. All right, so I'm going to make a really quick table so that I can order and I can view all of these ordered pairs. All right, so I'm going to create a table really quick. All right, so here's my table. Now I'm going to start extracting all of the ordered pairs. So the first ordered pair that I came across was my critical point, which was negative 1, 2. So looking at this here, I had negative 1, 2. But again, the conclusion that we came across is that this is not in the domain. So I'm just really quickly going to draw a line through here saying, hey, even though it's a value that we have, doesn't satisfy the domain, therefore we're not going to be able to use it. The next ordered pair, according to curve 1, was the ordered pair for 0, 0 and for 0, 5. So I'm going to write those here, 0, 0, 0, 5. Nice. Going to go to the next curve, which was curve number 2, find all of those ordered pairs. So I have 0, 5, I already have it here. I have a new one, 3, 0, and a new one, 7/5 and 8/3. All right, that one was here. All right, nice. And the last one, I have 0, 0 and 3, 0. That's 0, 0 and 3, 0, so they're already there. So all I need to do is find the values for these ordered pairs. Now, if you were following along, then we already have these values here. This value is 7, according to this. This value is negative 8. The value for 3, 0, that is negative 11. And the value for 7/5 and 8/3 should be 9/5. So now we get to see all of these values, and again, all of these should be matching. 0, 0, that was 7, and 3, 0, that was negative 11. That's good. So again, the first one that we found here was the critical point, but the critical point didn't give us anything valuable, so again, we discard it. On here, all we need to compare are z values now. Which is the largest, which is the smallest. All right. So smallest here, I see min, and largest, which is 7 here, I see a max. So f of xy has an absolute maximum of 7 at the point 0, 0, and an absolute min of negative 11 at the ordered pair 3, 0 within the given region. Now again, this statement is what I want to see at the end of the day. I want to see this statement. This statement just summarizes all the work that you did, and it condenses it really nice. All right, so in lieu of all of my mistakes, I'm actually going to stop it right here for today, and we'll continue on section 14.8 either later on today or tomorrow or Wednesday. All right, so I will see you all then.